All right, Hoover High AP Chemistry. This is lesson 61, day 61. It's the first lesson on equilibrium. And we will, this is due on Monday, December the 8th. We'll cover the rest of equilibrium on that day. And so equilibrium is simply the balance in a chemical reaction. How far does it go from reactants over to products? Or where does it find the spot, the happy place where it likes to stay? So reactions don't all go from 100% reactants to 100% products. Many of them stop halfway in between. In fact, most reactions will do that, or will do it under certain circumstances depending on the temperature and so forth. So what we're going to do is talk about how you figure out where that balanced place is, where that happy place is, right in the middle of the reaction. Okay, the first thing is to understand the central equation is called the law of mass action, or your book simply refers to it as the equilibrium expression. And so the first questions are just to write some of those. So for this one, you're converting ozone into oxygen, but you can also go in the other direction, which is what the double arrow means. It can go from oxygen to ozone. And depending on the circumstances, it will depend on how much of the ozone you'll have left at the end and how much of the oxygen you'll have at the end. Okay, so this one would simply be this. Now a gas can use a concentration, an equilibrium constant, or it could be Kp, it could be for pressure. In this case, we're going to use Kc. Okay, and that's all there is to it. It's products over reactants. You take the coefficient and turn it into an exponent. Same there, and that's how you do it. Okay, go ahead and do the next one. Okay, and finally we will do one more here. These are all what are called homogeneous equilibria because the states are the same in each reaction. There's not a solid or a liquid mixed in there, or a gas and an aqueous, for example. Different states. Okay, and of course if we had a liquid, a pure liquid such as water or some kind of a solid, you don't include it in the law of mass action. And that's it. So what this is saying is that there's a constant. This is constant for this reaction. Whatever Kc is here is constant for this reaction. So you can put in different concentrations here, in this case of ozone and oxygen, and get the same Kc. But it's just saying that ratio has to always stay constant. This ratio here has to always stay constant. That's at a given temperature. If you change the temperature, you end up with a different value of a different equilibrium constant, a different value of Kc. All right. Next problem. A sample of hydrogen and iodine are mixed in a 1 liter vessel at a temperature of 430 degrees. Once equilibrium is reached, it is determined that 2.5 moles of HI, 0.25 moles H2, and 0.5 moles I2 are present. What is the equilibrium constant? So the key to this problem, as opposed to the ones we're going to get to next week where you have to kind of do a little some calculations to get to the equilibrium, all of these values are at equilibrium. If you're going to write this expression, the values you have to be at equilibrium, and these are at equilibrium. So it's simply going to be, we'll write the general expression and then we'll insert the numbers. Okay, and now we simply plug in the numbers. The 430 degrees is not a part of the problem as far as any number that you'll use for a calculation. It's simply telling you that the temperature is staying constant. Because if the temperature changes, this rate constant changes. So you have to be at constant temperature. The problem could have stated at constant temperature instead of giving you a specific temperature. Okay, so we'll go ahead and plug in. Okay, and now you just calculate, since it's a math equation at this point, you could have used parentheses instead of the concentration symbols. And that gives us a value of 50. So that's saying that the products the ratio of the products to the reactants in this formula is 50 times. The products are 50 times greater than the reactants, at least when you plug it into that formula. Okay. All right. All right, number 3, in the synthesis of ammonia from nitrogen and hydrogen, and there's the equation. Kc is 9.6 at 300 degrees centigrade. Calculate Kp at this temperature. So calculating Kp from Kac is just a simple formula, and this is it. Okay, so let's define this. So R is the gas constant, the same one we used in PV equals nRT. A temperature needs to be expressed in Kelvin. Anytime you use this R, you have to have the temperature in Kelvin, because there it is right there in the units of measure for R. It's Kelvin, K. You can't use centigrade, so it's 300 degrees centigrade, so we're going to add that to 273. Okay, and number of moles. The number of moles is simply the total number of moles on the reactant side moving over to the product side. So we'll put a 1 there just to emphasize that that's a 1. So it's 1 plus 3 is 4. There's 4 moles on this side and 2 moles on that side. So it's going to be a negative 2. You've decreased the number of moles by 2. So again, just total number of moles of all the reactants, then total number of moles of all the products, and how did that change? So it changed to be a negative 2. So I'm going to put that here. Okay, now we can plug into the equation. And that's how the equation would be written, and now you can just simply calculate. Okay, so we just plugged in the numbers. There's R, there's the temperature Kelvin. Remember to raise it to this power before you multiply by 9.6, and that's your final answer. Again, there's no units of measure on that. All right, let's move on to the next problem. Actually, I'm going to leave the next one for you to do on your own. Okay, so for number 4, the final answer is going to be Kp equals... Okay, so go ahead and work that problem, see if you get that answer. Okay, let's move on to number 5. Okay, number 5. Given the following information, and you're given 2 equations, 2 reversible reactions with their equilibrium constants, and they want you to determine the equilibrium constant for that target reaction. So this is just like Hess's law. In what you try to do, you try to find a way to combine these two to make this one. What's different is how you treat the equilibrium constant, what you do to it. It's different than Hess's law. Hess's law, you remember, we did with enthalpies. And the rules for how you treat the enthalpies, depending on what you do to these reactions, is different than this. So let's go over the rules for equilibrium constants. Okay, so there's 3 rules. The first one says if you reverse the equations, so A plus B to C, you turn that around so it's C to A plus B. If you remember in Hess's law, you would have put a negative sign in front of the enthalpy. You would have reversed whatever its sign is. Here it's not the same thing. So in this case, what you do is you take the reciprocal of the equilibrium constant. You don't need to understand why that is really at this point. Just kind of know what the rule is for that. The next rule is if you multiply through by a factor, so down there you see A plus B gives you C, and if you multiply everything by 2, then what you do is you raise the equilibrium constant to that power of whatever that coefficient is that you multiplied through by. And finally, when you finally do add the reactions, what you do to the 2 individual equilibrium constants is you multiply them. Okay, so we'll go ahead and use that to solve this problem. Okay, so I've rewritten my equations down here. I multiplied 1 through by the factor of 2. That squares the equilibrium constant of 8 to 64. I reversed number 2 down here. That means the equilibrium constant, the 12 here, you take the reciprocal, you flip it. Alright, so now let's go ahead and be sure that these two add up to this. So I have on this side of this arrow a 2H2, and on the left side of this arrow I have a 2H2. This is why I like to circle the arrows, because you see they look like they're lined up, but they're not. This one's on the right side, this one's on the left side, so you want to be sure you see that. So that means they're going to cancel out like that. Okay, and over on this side, let's see, nothing else cancels, so over on this side we have 2HF plus this. And over on the right side, we have the 2F minus. And we also have the H2C2O4. And if we compare this with our target, it does match up. So now, since we added two equations, what we do is we multiply these two KCs. So you're going to have 64 times 1/12, and that's going to give us an equilibrium constant of 5.3, and that's the final answer. Okay, so done very much like Hess's law. It's just the rules for equilibrium constants are different than the rules for enthalpies and how they change when you do this, but you do everything else exactly the way you did Hess's law. Okay, let's move on to some of the book problems. So down here it says do the following problems from your book. You don't need to copy the question down unless you feel like that helps you, but explain the answer completely. Don't just give me a number answer. And there they are. So 21, 23, 24, and 29. All right, we're on 15.21 in your book. It's on page 660, so you're really deep into a college chemistry book right now. All right, so at 1,000 degrees, the equilibrium constant for pressure is 1.85 for this reaction right here. So that's the only thing you really need to just write down the data and the reaction on your paper. You don't have to copy every word of the problem. And then they want to know what is the value of Kp for this reaction. So it looks like what they did is they flipped it around. So similar to what we did on the last problem. So they want you to tell what the Kp is for that. What is the value of Kp for the reaction, this one? And that looks like they did what we did on the last reaction. They multiplied through by 2. So they want you to tell how that changed. And finally, what is the Kc? So you're going to have to go to the formula for Kp to Kc. In this case, you're going in the other direction. You're going from Kp to Kc. All right, so let's go ahead and write that down. Okay, so when you write it down, just write down the essential information, temperature in Kelvin. Again, temperature doesn't play into this at all other than to let you know that it stays constant. So the first one they are asking is they're reversing it. So we're going to do A is right here. We're going to flip the side back and forth here. Okay, so there we go for that. So this right here, we could go ahead and write the Kp was 1.85. So when we reverse it, it's going to be the reciprocal of that. And that gives us this. And let's get on screen there. It gives us 0.54. Okay, and that's all there is to that question. Let's go on to B. Now they're going back to the original equation. They're multiplying everything through by 2. So what they're going to do is take the Kp value and square it. Alright, and for C they want us to find Kc, so this is what we're looking for. And we had the formula earlier. Okay, so we just need to do a little algebra here. We can take this whole portion of the equation and just divide through by it on both sides. And now we can just rewrite that. Okay, and now it's just plug in the numbers, so it's going to... Alright, so we've rearranged this equation to solve for Kc. Again, the question is asking for us to use part B here, not the original equation. So we want to be careful on that. So Kp for part B is 3.45. Over RT. And the temperature is 1,000. It's already in Kelvin. And the change in moles, you have 2 here and 1 there on the left side. That's a total of 3. Over here you have 2. So it's going from 3 to 2. That's a -1 is the change in number of moles. Right there. So now we go ahead and plug those numbers in to the equation, and we end up with 3 sig figs 281 for the value of Kc. Kc equals 281. Okay, and that is your answer. Alright, question 1523. It says the following equilibria were attained at 823 Kelvin. And it gives you 2 equations along with their equilibrium constants. Based on these equilibria, calculate the equilibrium constant for this being the target reaction right here, and at the same temperature. Again, the significance is that the temperature didn't change, so those values don't change. Alright, so you should go ahead and write all 3 of these equations down along with the equilibrium constants. Okay, so I've written all 3 equations, and we're going to do this one similar to the one we did a little bit earlier. A couple of instructional points here. You do not need to write the equilibrium equation, the law of mass action, for this, but if you did, you would not include cobalt oxide because it's a solid, and CO over here is, that should be C small o. That's cobalt is a solid there. And also you find a solid with cobalt oxide again here. And cobalt solid here. So you would not include those in a law of mass action if you were writing it. Okay, and finally, let me just introduce you to my little shorthand way. You won't see this anywhere else, of writing a double arrow. I just write it like that. That way you do it, you don't have to pick up your pencil. It's just a couple quick strokes and you've got a double arrow right there. So that's just represents a double arrow. Okay, so we have equations 1 and 2. So let's circle our arrows. And what do we see? We see we have H2O. The only place we see it in either of these first 2 reactions is on the right side of the arrow, and it's on the right side of this arrow. So that tells us that we don't want to reverse this equation at all. The other thing we notice is we have all coefficients of 1. Everything is a coefficient of 1 in all 3 equations, so you're not going to multiply through by any factors. So it looks like the first reaction just stays the way it is. For the second reaction, we see CO2 on the left side of the target equation arrow, and we see it on the right side of equation number 2. So we're going to have to turn that around. Let's also be clear of this. This is carbon monoxide. It's a carbon and an oxygen, CO. This is cobalt. The second letter is lowercase. That means it's not another element, a different element. It's part of the same element right there. So CO is cobalt. Carbon monoxide, cobalt. Okay, so we're going to need to turn around the second equation. So I'm going to go ahead and write the first equation anyway, just to keep them together. I generally do that. It takes a little time. But I'm in no hurry. Okay, there's my double arrow. Since we're really not writing law of mass action, the states don't really come into play, so I'm just going to omit them just to save a little time and space. Okay, so that's equation number 1. I just copied it straight up. And for 2a, just means my second version is the A's of this. So we're going to reverse it. So CO and CO2 come over to the left side. And CO and cobalt oxide and carbon monoxide come over to the right. Okay, so let's double check my work. Okay, so when we reverse, what happens to this number? Nothing happened to this number because we didn't change anything. But when we reverse this, we take the reciprocal. Okay, so this is going to still be, this first one is still going to be this. This one is going to be this. Okay, now let's see if these two add up to this one up here. So H2 in our target appears on the left, and the only place it appears is in 1A on the left. That's good. CO2 appears on the left, and in these equations it appears on the left. That's good. CO appears on the cobalt oxide, COO, cobalt oxide, appears on the right, and excuse me, let me go to my target. I'm sorry, cobalt oxide does not appear at all. Down here it appears on the right, and it appears on the left of 1A and on the right of 2A. That means it's going to cancel, and it needs to because it does not appear in the target equation. Okay, water. Water appears on the right of 1A, and it does appear in the target, so that's good. Cobalt appears on the right in 1A and on the left in 2A. That means it's going to cancel. And finally, the only thing we have left is carbon monoxide. CO is on the right of equation 2A, and it's on the right here. So these two, in fact, do give us H2 plus CO2 right there. And on the right, we have CO and H2O right there. So everything is good. So now we've added those equations. So when you add the equations, what do you do to these two? You multiply them. So it's going to be 67 times 1 over 490. And you can just run that on your calculator. 67 divided by 490. Okay, and you get this. Okay, and that is your final answer. Okay, or to sig figs if you want to do it because you only have 2 there, it could be this. Okay, that's what your book shows because of the sig figs there. All right, okay, let's go on to the next one. All right, so 15.24 is exactly the same type of problem as 15.23, the one we just did. So what I'm just going to do is give you the answer. There it is right there. So work it through and see that you come up with that answer. Okay, number 1529, this is our last problem. So they give you an equation there, and they say equilibrium is established. An equilibrium mixture of three gases has partial pressures. So these are equilibriums. That means you can plug them in to your law of mass action and come up with your equilibrium constant for pressure. They are in atmospheres, and so they're the numbers that they gave you. They want you to calculate the Kp. Again, in this problem, the 500 degrees is not relevant except to tell you that the temperature did not change. All right, so let's go ahead, and the way I wrote that out is like this. That just kind of write out a shorthand. Just write out the essential facts. You don't need to write every word of the question. So you write a law of mass action for pressure. It's exactly the same as it would be for concentrations, except it's pressure. So it's going to look like this. Okay, by the way, everything is in gas state, so no liquids, no pure solids, so everything goes into the equation. So there it is. And the way you write it is you don't put it in brackets when it's for pressure, so the reactant, excuse me, the product's going to go up on top. And then this 2 is going to square it, just like it would for concentrations. Again, you don't need to put it in parentheses or anything. And that one's also squared. And you just put a little dot, or put it, you could put it in parentheses to just indicate multiplication here. Okay, and there it is. So now you plug in the numbers. And I copied one down wrong here. It should be 0.28. It should be 0.28. That was copied wrong. All right, let me just check the others real quick. The others look good. All right. Okay, and that gives us 50.8. Sig figs were limited to 2 because of that right there, so that would equal 51. Okay, and that's how you do these. So this is just kind of an introduction to how equilibrium equations work, the law of mass action, the equilibrium equation, same thing. And we'll pick this up on Monday, December 7th, when we get back to school.